At the outset, I would like to convey my regards and sincere thanks to Professor Shang-Tung Tu for the invitation to speak at the meeting today, to Professor Lu for following up and his organization of the meeting, and to Professor Jin Yang Sheng for chairing the session and providing the introduction. The topic that I am going to discuss involves design of pressure vessels for storing hydrogen at high pressures and assuring integrity of the design. This is a very active topic of research today because of high interest in renewable energy that necessarily requires the capacity to store energy to smooth fluctuations in the amount of energy that is available, as well as the energy that is used during various parts of a single day. After a career that spanned over 5 decades in research and academia, working on problems related to fatigue, fracture, and creep, I've been focusing during the past 10 years on pressure vessel design for storing gases such as CNG, air, and hydrogen at very high pressures. Storage of hydrogen presents the most significant challenge in the design of pressure vessels because the susceptibility of ferritic steels to hydrogen embrittlement. My presentation will primarily deal with storage of hydrogen at high pressures. Several concepts and approaches that I will describe are equally applicable to storage of other gases as well. I currently serve as the president and CEO of WireTough Cylinders, a company located in Bristol, Virginia, that has been designing and making Type 2S pressure vessels. These vessels are made from a one-piece steel liner that is reinforced in the hoop direction with a jacket made from very high-strength wires with tensile strengths exceeding 2 GPa. Only the liner is in contact with the hydrogen, and significant fraction of the hoop stress is borne by the high-strength steel jacket. This produces a highly cost-effective and durable pressure vessel that is uniquely suited for storing hydrogen at pressures from 300 bar or more, and in fact, all the way to 1,000 bars. At the outset, I'd also like to acknowledge the collaborators in this work. From WireTough Cylinders, my colleagues Amit Prakash, William Thompson, Forrest Harless, and George Sharp. From N&R Engineering, Ian Miller and Vinod Nagpal. From Structural Integrity Associates, Dan Peters, Chris Tipple, Jeff Milligan. From High Pressure Materials Testing, Kevin Nyber. From Oak Ridge National Laboratories, Glenn Romanowski. And from Sandia National Laboratory, Brian Summerday and Chris Sanmarkey. The sponsors of this work are the U.S. Department of Energy, specifically the Energy Efficiency and Renewable Energy Office, and also the Commonwealth of Virginia, the Tobacco Commission Revitalization Commission. The short outline of my presentation would be I will make some introductory remarks that talk about hydrogen as a source of energy to achieve environmental sustainability. I will then talk about the technological challenges that are associated with it, which include cost-effectively storing and delivering hydrogen, assuring safety through structural integrity analysis and use of design codes, and then I will describe a case study of a design of a 765-liter capacity vessel for storing hydrogen at pressures of 875 bar or 87.5 MPa. And then I will close with summary and conclusions. Now, going back to potential applications requiring hydrogen storage, transportation is will be a prime user of hydrogen as an energy source. And in transportation, we have passenger automobiles, medium and heavy-duty trucks. We even have trains and possibly ships. Then there is backup and auxiliary power for data centers, large buildings, and manufacturing plants. Material handling, such as forklifts and warehouses and farm equipment. Bulk energy storage in power plants to balance power generation needs between peak and lean demand periods. reserve energy storage for mitigating power interruptions due to natural disasters. Now, if we look at the market for hydrogen storage tanks, by 2030, we expect that there will be 15,000 new hydrogen fueling stations worldwide, and at 10 cylinders per station to store 600 kilograms of hydrogen, we need 150,000 tanks. More than 350,000 hydrogen-fueled trucks will require 700,000 onboard tanks. Similarly, 50,000 hydrogen buses will need 50,000 hydrogen tanks. Trains and passenger ships powered by hydrogen is another possible application. Up to 200 steel, chemical, and automotive plants will be using hydrogen for heat and for power. 250 to 300 terawatt-hour surplus renewable electricity will be stored as hydrogen by 2030, needing 200,000 storage tanks. Now, if we look at design considerations for storing hydrogen, cost and safety are the dominant considerations. Costs are affected by materials of construction, manufacturing processes, production volumes, required inspection and quality assurance procedures for ensuring durability, expected service cycles, but built-in flexibility to future changes in usage. Safety is achieved by adhering to design codes. ASME Section 8 Division 3 KD10 for vessels designed to operate in hydrogen is based upon requiring a complete analysis of stresses due to manufacturing processes and service loading, initial design life estimated based on postulated flaws, which is a damage-tolerant design approach which has been used in aircrafts and nuclear pressure vessels for a long time. Certification of vessels similarly in service for extending their design life. Now, if we just focus for a minute on filling stations for hydrogen, what are the associated design goals? Pressure vessels are needed with capacities of 750 to 2,000 liters to safely store hydrogen between 500 to 875 bar that also meet the storage vessel cost target of less than $1,000 per kilogram of hydrogen stored. An estimated life of 20 plus years based on ASME Section 8 Division 3 KD10 requirements. These are requirements for fitness for service in hydrogen. Now, the approach that we have taken at WireTough is to basically use a liner that is reinforced with high strength wires. So in the liner selection, we to design cylinders that are about 10 meters or less in length, but have a capacity of 750 liters, the ID must be at least 350 millimeters or larger. Use of metal liners 350 millimeter ID are limited to pressures of 30 MPa due to a maximum wall thickness restrictions of 37.5 millimeter from the microstructural consistency or hardenability considerations, and B, the ability to reliably detect defects larger than 1 millimeter deep and about 5 millimeter long on the surface. The manufacturing processes consist of a wrap that is made from commercially available manufacturing processes consist of wrapping a commercially available Type 1 cylinders with multiple layers of ultra-high strength steel wires with strength levels that are greater than 2 GPa to significantly boost their pressure capability. As an option, auto-frottage wrap cylinders to lock high compressive stresses throughout the liner thickness to enhance fatigue life. The schematic of our design is as follows in this figure. You have the steel liner. The steel liner is reinforced with the steel wire wraps, and then you have a UV protective skin on top of that, and that essentially makes a complete cylinder system. So if we make a comparison and try to list some of the advantages of what we call as a Type 2S cylinder, which is the WireTough design, we have in construction materials, we use steel liners reinforced with high-strength steel wire wraps. Then the advantages are high durability, high impact and ballistic resistance, high fatigue resistance, and then using only off-the-shelf construction materials with reliable properties, then higher stress transfer from liner to the wrap. Drawbacks are these are heavy and suitable only for ground storage, where weight is not a significant consideration. So you would not be used for transportation purposes or for on-vehicle tanks. Type 2 vessels are basically steel liners that are reinforced with either e-glass or graphite fiber wraps. This also reduces hoop stresses in the liner, enabling high pressure capability compared to Type 1. And then also wrap material has low density. Among the drawbacks, low impact and ballistic resistance, low modulus of e-glass fiber requires a thick wrap, a weak liner wrap interface. Carbon fiber is expensive and has larger scatter and mechanical properties. Type 1 cylinders, the primary advantage is cost, but that too, with the rising prices of steel, is not going to remain an advantage for very long. All steel, the one-piece construction, it has good durability, but the use is limited to 300 bar hydrogen pressure and it has inadequate fatigue life per ASME Section 8 Division 3 prescribed methods in hydrogen for higher pressures, and is also very heavy. Now these are some test results for on Type 2S vessels. These are not vessels that are being designed for hydrogen, they're more for CNG and have a much thinner gauge liner as such. And as you can see, if you subject it to a burst test, you get a very graceful failure mode, which is a leak before break type failure. Then if you, at the bottom left corner, you have the vessel after it has been subjected to a bonfire test, and you can see that the integrity of the vessel, the liner, and the other structural part, which is the steel wrap, are essentially intact. Then if you look at the bottom right corner, you have the vessel after it has been shot by a .5 caliber gunfire, which has over 5 times the energy absorbed compared to .3 caliber gunfire on a carbon fiber cylinder. So if you were to compare a comparable carbon fiber cylinder, .3 caliber gunfire will cause as much damage as a .5 caliber gunfire would to a steel pressure vessel. Then in the upper right-hand corner, you have the exterior surface of a Type 2S tank with a machine notch after it had been exposed to salt water for 28 days while being pressure cycled for 3,200 cycles. And you can see that literally there is very little damage propagation as such. So the upshot of all this is that we do produce a very durable pressure vessel. Now, in designing these pressure vessels, there are obviously several technological challenges. When you use ferritic steels, and you have to use ferritic steels because of cost considerations, performance, you have to look at the performance of these steels in gaseous hydrogen. It has been known for a long time that if you have a defect, for example, in ferritic steels that is being exposed to gaseous hydrogen, you have several mechanisms of damage that are causing the cracks to grow faster, or essentially have environment-assisted cracking, which is faster than what you see in non-hydrogen or innocuous environments. Some of those mechanisms are hydrogen-enhanced local plasticity, reversible trapping of dislocations, hydrogen-enhanced decohesion. These are all that occur, and we have to basically test the material to make sure that we have properties that have been obtained under these high-pressure hydrogen conditions, and the measured crack growth rates account for some of these degradation mechanisms. The steels that are used are low alloy, high-strength ferritic steels, A372 grade J, that has a history of several decades of use for storage of hydrogen, although at low pressures. However, there are concerns about their use in the high-pressure hydrogen environment. So microstructure control to limit their strength and reduction in operating stress levels are necessary. Materials testing and modeling, as well as good design and improved NDE protocols, are all necessary to reduce the risks. Now, if we look at the microstructure of the liner material, which is SA372 grade J class 70 steel, it is quenched and tempered. The typical yield strength level is about 700 MPa. The tensile strength is on the order of 880 MPa. Percent elongation is 21%, and reduction in area is 60. And if you look at these properties compared to the standard specifications for SA372 grade J class 70 steels, these materials that we have used in deriving the properties under hydrogen conditions sufficiently exceed those properties. So they meet the minimum requirements. Now, another test that has been done at Sandia National Lab, we all understand from our previous experience that the susceptibility to hydrogen embrittlement does depend to a large extent on the ultimate tensile strength of hydrogen. So Sandia National Labs has done a lot of testing of fracture toughness as a function of tensile strength for specimens that were exposed to 100 MPa of hydrogen. And what they find is that once you decrease the strength levels to below 900, increase the strength levels to below 950 MPa, there is a sharp drop in the fracture toughness value. So that indicates that the susceptibility of hydrogen embrittlement is much higher when the strength levels are greater than 915 MPa. And therefore, that has been established as the upper limit of the ultimate tensile strength for ferritic materials that are used in hydrogen storage vessels. We have done, and so has Sandia National Lab done, a lot of materials testing to document the fatigue crack growth behavior in pressure ranges from about 10 MPa to 100 MPa of hydrogen. And this has been done at various load ratios. And the reason for doing it at various load ratios are the service cycles can be partial unloading or they can be full unloading of the pressure vessel. So depending on what the minimum pressure is, the load ratio or the stress ratio that the vessel is subjected to does change. And these test results are for R equal to 0.5, ranging from R equal to -1, which is for WireTough cylinders, as we will see later. You have a high degree of compressive stresses. So when the pressure is reduced, the vessel actually goes into compressive stress state. So we have to document the fatigue crack growth behavior that is ranging from high load ratios of 0.5 to low load ratios of -1. And we can see that there is a difference in the fatigue crack growth rate behavior as a function of delta K. And also for reference purposes, we plot here the value of fatigue crack growth rate as a function of delta K for air. And this is at several load ratios. In air, the steel is not susceptible to changes in fatigue crack growth rate with load ratio, but certainly when you talk about high pressure hydrogen, it is a big effect. So these results basically are the basis for the properties that we use to estimate the life of design life of cylinders, and we will use them very extensively in the future. Now, besides load ratio, we also have to be concerned about the effects of frequency. The effects of frequency on the fatigue crack growth behavior are important because the service life, in service, the frequencies are very low, whereas when you do accelerated tests in the lab, the frequencies can be anywhere from 10 hertz to about 0.1 hertz. What our data has shown, and also what Sandia National Lab has shown repeatedly, that when you test materials at 1 hertz frequency or 0.1 hertz frequency, you capture the essence, or you capture the high fatigue crack growth rates. So there is no need to really decrease the frequency further than 1 hertz to 0.1 hertz. 1 hertz is, of course, a very acceptable test frequency for conducting fatigue crack growth tests. So that is typically used more frequently in during testing. Then this is the effect of load ratio, and we can plot the effect of load ratio at different values of delta K, and you can see that between minus 0.1 and about 0.2, there is very little effect of load ratio. But once you go beyond R of 0.2, you do see an increasing effect of load ratio. So that is something that we have to keep in mind when we do our testing, and we also when we use test data in application. Now, hydrogen pressure is another variable that can affect the fatigue crack growth rate, and it is important to document the effect of pressure on the fatigue crack growth behavior. And here it is. You can see at delta K of 10, at delta K of 20, and delta K of 25, you have the fatigue crack growth behavior at different values of hydrogen pressure. And we observe that the fatigue crack growth rate increases significantly with pressure up to 45 MPa and then appears to saturate. For delta K less than 10 MPa root meters, fatigue crack growth rate is not significantly affected by pressure. So all this data that has been generated by WireTough under the sponsorship of DOE, as well as data that has been generated by Sandia National Lab, has gone into the formulation of the ASME Section 8 Division 3 master curve for service and hydrogen. This is the ASME Code Case 2938 that tells you how to estimate the crack growth rate, which is assumed to be a function of the load ratio and delta K. And basically these equations describe are the values of the material constants that are used in this fundamental equation that is at the very top. And we see a transition behavior in which where we see that beyond a certain delta K, the crack growth rate crack growth rate curve slope decreases significantly compared to when the delta K is less than that transition delta K. And all this is very evident in this plot here that shows how the DADN changes with delta K as a function for various load ratios ranging up to R.8. And you can see that in each case there is a delta K level at which this transition occurs. And when you go to R.8, for example, the transition occurs at a much higher delta K than it does when the R is equal to 0.1 or less. So if we were to summarize the effects of load ratio, loading frequency, and pressure on the fatigue crack growth rate behavior of A372 grade J steels, you would find that the load ratio effects in high pressure gaseous hydrogen appear to become significant for R.2, and especially in the pressure range of 100 MPa. In the range of -1 to 0.2, FCGR behavior is almost the same. The effects of decreasing high loading frequency beyond 1 Hz on the FCGR behavior in high pressure gaseous hydrogen are marginal. Thus, 0.1 Hz to 1 Hz is a suitable range for testing while producing data relevant to hydrogen design, relevant to design of pressure vessels for storing hydrogen. The available data show that the fatigue crack growth rates in gaseous hydrogen do increase with increasing pressure. The magnitude of this effect seems to be highest in going from air environment to 10 MPa hydrogen pressure and appears to saturate at 45 MPa level. Thus, at delta K less than 10 MPa root meters, pressure appears to have minimal effect on the low delta K. At the low delta K, also at delta K of 10 less than or equal to 10 MPa root meter, pressure effects appears to have minimal effects. Then we've also done, with the help of Oak Ridge National Lab, some testing on the wires that are used. Wires are not exposed to hydrogen, but because there could be some low concentration levels of hydrogen in the environment surrounding the vessel, and it is important to document how the wires would perform under those conditions. And the extensive amounts of testing of the wire at different stress levels and also at different hydrogen pressure levels or concentration levels measured in parts per million by weight, we do not see very significant effects on the strength of the wire. So for all practical purposes for design, we can assume that the steel wires that are made out of very high strength steel are in fact not as susceptible to hydrogen. Then we move to the stress analysis of the liner, which is necessary part of the ASME certification. And the stress analysis must account for very accurate dimensions of the liner, residual stresses from the wire winding, must account for residual stresses from autofrettage. Autofrettage is a process in which we subject the vessel to pressure levels of almost 2 times the maximum operating pressures. And what that does is it basically plastically deforms the liner. And when you remove the pressure, the wire wrap, which remains elastic, collapses onto the body of the liner, and it creates a lot of compressive stresses that actually decrease the maximum stress that the liner wall sees when it is subjected to the service pressures. So we have to also then account for service loading from maximum to minimum service pressures. The life, we have noticed, is dictated by surface flaw in the main body of the liner, and we assume surface flaw size that is equal to less than the size that is 100 detectable, 100% detectable from the ultrasonic techniques that are used to detect flaws. And this slide here basically shows some of the equations that are used for calculating the stress intensity parameters for these type of flaw shapes and geometries. Now I'm going to go directly to the life of the vessels. If we make comparisons of fatigue lives of autofrottaged and non-autofrottaged cylinders for hydrogen storage, we get the following results. But let me back up a little bit and talk about autofrottage and non-autofrottage. Non-autofrottage cylinders basically are not subject to the very high autofrottage pressures during which the liner goes through plastic deformation. They're basically, but still there are compressive stresses that are involved from the wire tension during the wiring process. So even a non-autofrottage cylinder does experience some compressive stresses at zero pressure, and those compressive stresses have to be overcome by the service pressure before it goes into a tensile range. On the other hand, the autofrottage pressure can be 2-3 times higher than what you would generate from just the wire tension, and it can reduce the maximum stress in the liner very significantly. So if we look at vessels that have been wound by 40 layers of wire, 48 layers of wire, 54 layers of wire, and 60 layers of wire. If we look at autofrottage and non-autofrottage vessels, so no means it has not been autofrottage, yes means it has been autofrottage. The computed cyclic stress level for 40 layers of wire for non-autofrottage is 321 MPa, and for autofrottage it is only 218 MPa. So if we calculate delta K at the deepest point, delta K in MPa root meters is 13.94 for the 321 cyclic stress level, and only 9.46 for the 218 cyclic stress level. We find that if we do these calculations for 40, 48, and 54 layers of wire, the sweet spot is at 48 layers of wire, where after autofrottage, the resulting delta K for a crack size that can possibly be missed during non-destructive inspection is about 7.32 MPa root meters. And if we start with that delta K, we will easily reach our goal of 20 years of design life during service. So 48 layers in this case is what we find is our sweet spot. Now this is a picture of the vessel that has been produced in our manufacturing facility. You can see it is 765 liters, so it's about 10 meters long, and the outside diameter is about 450 millimeters, and it can store hydrogen up to 875 bar, and it can deliver the design life of 20 plus years in high pressure hydrogen. So with that, I would like to move to the summary and conclusions. Type 2S vessels consisting of a metal liner wrapped with high-strength steel wires and subjected to autofrottage are shown to be suitable for storing hydrogen at pressures of up to 875 bars. The fatigue crack growth rates under negative load ratios were shown to be comparable to the rates at low positive load ratios of less than 0.2 in high-pressure hydrogen environment for SA 372 grade J class 70 steel. I also want to point out that I've been interchangeably using A372 versus SA372. A372 refers to an ASTM standard, and SA372 refers to an ASME standard for the same material. So we can use those terminologies interchangeably. Maximum allowable stresses in the interior wall of the hydrogen storage vessels must be lowered significantly in comparison to those for storing benign gases to account for hydrogen-assisted crack growth. There is need to inspect for crack sizes that are no longer than 2 to 3% of the wall thickness instead of the current industry practice of 5% to facilitate the achievement of design goals. Also, there is need to develop reliable techniques for inspection of vessels during service for recertification. There is need for developing inexpensive steels that are more resistant to environment-assisted cracking. With that said, we are currently involved in projects that would allow us to have pressure vessels that are almost 2,000 liters in size and would be able to sustain 800 or 900 bars of hydrogen pressure. So it's an exciting field. It certainly is very consistent with my background that I've amassed over 5 decades in the field of fractional mechanics. And I'm so glad that towards the twilight of my career, I have the ability to apply my knowledge to design something that is new and innovative. So thank you very much for your attention. And if any of you have questions, you're more than welcome to email me, and I will respond to your questions.